Welcome to our presentation on trajectory inspection, a method for iterative clinician-driven design of reinforcement learning studies. I'm Christina G, and this is joint work with Michael Oberst, Sanjat Kanjilal, and David Sontag. I have no disclosures. From this presentation, I hope you'll learn how to use trajectory inspection to gather observations on where model-based reinforcement learning models may not align with clinical intuition. I also demonstrate how to formulate hypotheses about why these observations occur and what design choices may be associated with them. Reinforcement learning has become a popular tool in healthcare, with recent applications in sepsis, acute hypotension, HIV, and many other diseases. Reinforcement learning applies to any sequential decision-making setting, that is, any process where there is a state and an action and then it transitions to another state. The action from each state is chosen based on a policy that is dependent only on the current state, and the transition is only dependent on the current and state and action. This is called the Markov property. After a sequence of transitions, an outcome or a reward is reached. This outcome could be positive or negative, and the goal of reinforcement learning is to optimize for the maximum outcome. In reinforcement learning, a better policy might be learned, where a different action could be taken at a certain time step in the sequence, leading to a hopefully better reward. In trajectory inspection, we examine whether actions recommended by the reinforcement learning policy differs from what is observed, and the trajectory that is predicted afterwards, since that is an explanation for why the RL policy picked that action. Trajectory inspection can be applied to any model-based reinforcement learning setup. Model-based reinforcement learning first learns a model of the dynamics, that is, how the transitions happen. Then it finds an optimal policy given those dynamics. In trajectory inspection, the first step is to identify trajectories with surprisingly aggressive treatment or surprisingly positive outcomes. Then we can look at these trajectories and what will happen under the reinforcement learning model. That is what happens when the reinforcement learning action is taken and the model is rolled out in a new trajectory based on the dynamics. This new trajectory is called the rollouts. We also look at the context of the patient's stay from the clinical notes. Finally, we can formulate and investigate hypotheses based on these observations. These can then inform a better problem design, and this process can be iterative. For our work, we replicate the reinforcement learning for sepsis setup from the Komorowski et al. Paper. The dataset consists of 20,090 intensive care unit admissions from the MIMICS-3 database. The trajectories are discretized into 4-hour intervals. That is, the average or maximum for each feature is taken across a 4 hours time span. Up to 20 steps of the trajectory are taken, roughly around the time of sepsis onset. The actions consist of 25 bins that range from no treatment to the lowest quartile to the highest quartile, looking at fluid and vasopressor levels. The 47 state variables include demographics, vital signs, lab test results, ventilation settings, and treatment information. Finally, there is a reward at the end of the trajectory, positive 100 or minus 100 based on the 90-day mortality. Now we will look at the two heuristics used to identify trajectories. In the first heuristic, we identify reinforcement learning recommended actions that are rarely observed and much more aggressive than what is observed in clinical practice. On the left, we plot the states on the x-axis, and the y-axis is the proportion of times the reinforcement learning action is taken from that state. We investigate states that are on the right, where the reinforcement learning action is rarely taken in practice. 10 of those states are plotted here. On the x-axis of the other two plots are the fluid and vasopressor levels in their action. The green dot represents the most commonly observed treatment, while the blue X represents the RL recommended action. The red arrows on top show that the treatment at that state is much more aggressive under the RL policy. so we examine samples from that state. In our second heuristic, we look at trajectories, where the difference between observed outcome and the outcome predicted by the model under the reinforcement learning policy is large. Specifically, we look at samples that start from this state where the model believes that the patient will then survive, but in actuality, the patient died. This is suspicious because it is unlikely that the patient was able to survive, and this means that the model may have erroneously overestimated the likelihood of surviving from taking that action. Now we will look at some samples that we selected using these heuristics, starting with the context of their clinical notes. For this first patient, she was transferred to the intensive care unit following coronary artery bypass graft surgery. The patient recovered well, was extubated, was gently de-arrested, and released from the intensive care unit following the first day. And after a few more days, the patient was discharged home in good condition. Here we look at the trajectory for this patient. The actual trajectory is shown in black, and we plot the heart rate, systolic blood pressure, diastolic blood pressure, white blood cell count, fluids, and vasopressor levels. The red dotted lines represent the reference range. The actual trajectory ended in a positive outcome, as shown by the green dot. The model-based rollouts also end in positive outcomes, and they are shown in blue, green, and purple. The reinforcement learning policy suggests unnecessary prolonged use of aggressive treatments. For this patient, they did not need such aggressive treatment since they were recovering well, and yet some of the rollouts continued for a long time with aggressive treatment. Another thing that was unrealistic was the expected discharge while on vasopressors or excessive fluids. A patient is usually removed from such treatments before being discharged from the intensive care unit. The response in the state variables is also inconsistent with the action. High levels of vasopressors are administered in the purple model-based rollout as step 8, and yet the blood pressure did not rise until step 10 for this patient, when we would expect the effect to be much more immediate. For the next patient, we find someone who was admitted to the intensive care unit with sepsis and pneumonia. A chest exam showed that the patient likely had stage 3 lung cancer, and the patient ultimately died of respiratory failure. It is unlikely that any fluid or vasopressor treatment is able to save this patient. The actual outcome is shown again in black, and it ends with the negative outcome. This trajectory was also censored because it was actually much longer than 20 time steps. The model-based rollouts are in orange, purple, and pink, and they all end in positive outcomes. We also see some of the rollouts actually terminated at the first step, which is surprisingly early. For such a patient, we would expect that the more treatment to be recommended and for their ICU stay to be much longer. Now we can formulate and investigate some hypotheses based on our observations. The first is our hypothesis that the model is biased towards early discharge. This is actually a much more general phenomenon. We infer that this occurred due to the censoring with terminal rewards heuristic. That is, if a trajectory was longer than 20 time steps, it was truncated at the 20th step, and the reward was applied there. So if a patient actually required much more treatment before discharge, it would seem as if the patient was discharged from that intermediate state. In addition, the model, we can see here in blue that the model knows when it reaches the 20th time step that it has to terminate, but the model is not aware of this because the transitions are Markov. And therefore, in orange, we can see that the 20th time step, the model does not predict that all samples end. Instead of the gradually increasing rate of termination in blue, the orange line is more flat. And to match the overall termination probability, the model is forced to overestimate the terminal transition probability at earlier time steps, leading to the bias towards early discharge. We also generated some other hypotheses. First, the clinically implausible discharges at high levels of treatment or from states where the patient is unstable may have been due to the sensory mechanism we just discussed or discretization. Because the treatment information is being captured over a 4-hour interval, it may seem to the model that the patient was on treatment for the entire 4 hours and then discharged. But in reality, the patient's treatment may have ended at the start of the 4 hours, and so they were actually weaned gradually, and that they were discharged from a much lower level of treatment. We also saw that the model does not accurately capture underlying conditions. Lung cancer is not one of the state variables, and it certainly affects both the treatment choices and the outcome. The high vasopressor doses that were observed in the aggressive treatment may have been linked to small sample sizes. These high doses may have only been observed a few times, and just by chance, these observations are always in patients who survive. This leads to the model erroneously believing that these high doses are actually beneficial. Finally, the reward function may be misspecified. The reward function only optimizes for 90-day mortality. However, doctors may optimize for patient comfort instead. In conclusion, we hope that our method will help with checking that reinforcement learning models correctly anticipate the impact of their policies. If they don't, then our method can help with improving the model. We also hope that by visualizing trajectories and inspecting the clinician notes, we can bring clinicians into this iterative process and incorporate their feedback into improved model design. This would help both in building trust and in making sure that these models are useful if deployed. So any model that reflects patient dynamics accurately will hopefully be trusted more during deployment. Thank you for listening to a presentation, and I'm happy to take questions.